Very much. Ladies and gentlemen, the title of my talk, as you can see, is devoted to generalized so-called intermediate quantifiers. The main topic, what does it mean, validity of syllogism and so on, you will learn during my talk. So first, concerning generalized quantifiers. Generalized quantifiers or quantifiers in logic appear already and have been studied more than 2000 years. The theory of quantifiers and syllogisms with them has been established by Aristotle already 2000 years ago. Since then, only two quantifiers for all and exist have been studied and have been used. But in 1957, Mostowski, Polish logician, introduced the concept of generalized quantifier, and his work has been followed by many people, and especially by Per Lindström in 1996. So let me say, quantifiers appear in natural language as a special expressions or words which precede and modify nouns. They really exist. And the meaning is that they specify quantity of elements in a domain of discourse which bear some property. Here are two examples. A few beautiful roses are standing on a wooden table. Many red flowers were damaged by strong wind, and many other kinds. Per Lindström introduced a very general concept which he calls general quantifier of type K1 to Kn, where K1 to Kn are natural numbers. And his definition is that it is a function with a symbol which to each set assigns a fuzzy relation. And this fuzzy relation is determined in such a way that here A1 to AN are formulas, which are properties of some elements, and we can form a so-called satisfaction set in a given model. Of course, everything is with respect to some model. And this satisfaction set is a set of all elements which bear the property A1 or 2AN. So such a quantifier is true in a degree A if and only if these satisfaction sets are in this fuzzy relation QM. In natural language, mostly we appear and are studied quantifiers of type 1,1. It means that they have two properties, B and A. And here is a typical example. Many Q, many is a quantifier Q. Thick books on the big bookshelf, which is a property B, are very interesting, which is a property A. Peterson wrote a very interesting book in which he introduced and studied so-called intermediate quantifiers. Typical intermediate quantifiers are here, a few, almost all, and so on. And we have developed a mathematical model of these intermediate quantifiers. We argue that they behave similarly as classical quantifiers for all and exist, but quantification is done over a small class of elements, and this small class of elements is specified using special expressions of natural language. Therefore, the theory requires higher order logic, and in our case, because these are fuzzy quantifiers, higher order fuzzy logic. Intermediate quantifiers in our theory are interpreted by special formulas. This is the formula which I think many of you have already seen. Very briefly, it is a formula which says that there does exist in this interpretation fuzzy set Z such that this property, this implication holds true, and at the same time, the evaluation of the measure, this measure is evaluated by certain evaluative expression. Here you can see the symbol B, the /Z. This means cut of a fuzzy set B. It means that fuzzy set, from fuzzy set we eliminate all elements or singletons. It means elements with their truth values which are not equal to the corresponding elements of the fuzzy set Z. Here we evaluate this cut of a fuzzy set of this fuzzy set B with respect to the whole fuzzy set B. From intermediate quantifiers, we can form so-called graded square of opposition. Here, this is the square, and you can see here are various kinds of intermediate quantifiers starting from all and finished by some. And here, arrow means the relation of super-artan and sub-artan. It means that super-artan implies sub-artan. So this is implication from top to down. And here this dashed relation is a relation of contrary. It means that these two expressions cannot be both true, but they can be both false. Here, this dotted line means relation of subcontrary. It means that these two expressions can be both true, but cannot be both false. And here, these lines express the relation of contradictory. It means that these two expressions can be neither both true nor both false. The cube of opposition is extended by other possibility, the square of opposition is extended by other possibilities. If I written here, you can see all these quantifiers have the form that here B is in positive way and A possibly can be in negative way. But we can extend it in such a way that both can be in negative way. It means that this is quantifier negation of B and negation of A. And the formula is more or less the same, but here instead of formula B, you see the formula negation of B, and instead of formula A is a negation of A. Similarly, for other quantifiers, where here is classical quantifier existential, again taken over small class of elements. Then we can form special quantifiers, intermediate quantifiers in negative form. Classical quantifiers, I think this is quite clear. And similarly, non-classical quantifiers, again, starting from almost to most and many. From this, we can form a cube of opposition. So the front part of this cube of opposition are our quantifiers, which you have already seen, and the back side of this cube of opposition are new quantifiers in negative forms. Again, the meaning of these lines is the same as said. So this is a line expressing relation of subcontrary. This is line relation. This is line relation of contrary. Here, this is a line of relation of subcontrary, and here this means contradictory, and here this arrows means artan and subartan. In general, we can say that square and cube of opposition reveal deeper structural oppositions and connections among propositions. So square of opposition may contain negative consequent but not antecedent, while cube of opposition may contain both negative antecedent as well as consequent. Both square as well as cube of opposition give rise to related intermediate logical syllogisms. So a logical syllogism is a triple of expressions. Each of them is a quantifier in, say, instant meaning. Here, these are two antecedent, first and second, and conclusion. And this syllogism or syllogisms are organized into 4 figures, depending on the position of S is a subject, and P is a property, and M is a middle formula. So 4 figures of this syllogisms. A syllogism can be true in some models and false in other ones, but if it is true in all models, then it is valid. Syntactically, it means that this implication is provable. Semantically, it means that for each model, this inequality is true. And now the question is how to verify validity of syllogism. So, of course, we have these two possibilities, syntactical and semantical, but this requires either quite laborious formal proving, or formulation in arbitrary model. And Peterson suggested so-called rules using which we can verify whether a given syllogism is valid or not. Let me emphasize that this research, which I'm presenting here, is very important, and it is indispensable for real artificial intelligence. Here is example of invalid syllogisms. Almost all M are P, or most S are M, and from this we conclude that some S are P. But here on this figure, you can see that such a syllogism is not true, is not valid, because the subject can be such that the part which does part of property M and which does not have property P covers most part of S, and S and M are empty, or intersection of S and M are empty. Yes, this is arbitrary, of course. Otherwise, it would have no sense. So we asked ChatGPT if it is true that the above syllogism really implies some SRP. And the result or the answer of ChatGPT was the following, that it is very likely that some SRP, though the argument is not 100% logically airtight, since almost all allows for a few exceptions. In practical reasoning, this is again ChatGPT says, the conclusion some SRP is valid based on high probability. This argument cannot be accepted. It is untenable, and such answer of ChatGPT is pointless. Simply, either the elements have the property S and property P, and either they have both of them or not, but no probability is at play. So it has no sense, such an answer. Therefore, it is clear that ChatGPT does not contain logical formalization and cannot be used for logical reasoning. This is example of a syllogism related to graded cube of opposition, and such a syllogism, it is of figure 3, it is true. So most people who do not smoke do not suffer from asthma. Most people who do not smoke have not yellow teeth. Some people who have not yellow teeth do not suffer from asthma. So it is example of syllogism which is true. Peterson, as I said, suggested originally 6 special rules using which we can verify whether a given syllogism is valid or not. We have studied these syllogisms for positive quantifiers, and here in this talk we will show that they can be also introduced for negative syllogism from the backside of the cube of opposition. Important is so-called distribution index. Let me remind that in the definition of the given quantifier, we use evaluative expressions. Mostly we use these evaluative expressions whose extensions, which are fuzzy sets, have this form. This is fuzzy set for not small, fuzzy set for very big, fuzzy set for extremely big, and so on. And it turns out that this so-called distribution index is nothing else an infimum of support of the given evaluative expression. So, for example, this element, this element, this element here, this element, and this element. And on the basis of that, we reformulated original suggestion of Peterson, which was otherwise provided in natural language. And in fact, as I said, he introduced 6 rules, but only 4 of them are sufficient because the remaining 2 syllogisms are consequence of these 4. I will not go into the details. So there are 2 rules of distribution which relate or check whether the distribution index of the given syllogism is fulfilled, and 2 rules of quality here for the second phase. So they have, you can see that there are some negations of them. What is necessary to prove that if a given syllogism is valid, then it satisfies all 4 rules. And if a syllogism satisfies, arbitrary syllogism satisfies all 4 rules, then it is valid. We have proved that this is really true for positive syllogisms, and for negative syllogisms of figure 1, we proved only figure 1. And we proved that the negative syllogisms are valid if and only if they satisfy the rules F1 to F4. And these are codes for syllogisms. If you remember these letters A, P, T, and so on. I will go back and show you. So these are, for example, P means almost all are not, almost all not B are not A, T, most not B are not A, and so on. So this is the theorem. And here is example of syllogism from the area of well-being. Almost all people who do not get regular social support do not feel emotionally content. Most people who do not get regular social support do not maintain healthy daily routines. And from this, we conclude that some people who do not maintain healthy daily routines do not feel emotionally content. This syllogism satisfies all the extended Peterson rules, which were on my previous slides, and therefore such a syllogism is valid. Here is another syllogism, but this syllogism is invalid because it does not satisfy the rule number 2. So, to conclude, we introduced the graded cube of opposition and suggested to extend the original Peterson rules for verification of validity of syllogisms with negations. We proved that all valid syllogisms with negations verify the extended Peterson rules, and for figure 1, it is also the other implication. So what remains is to extend our theorem for the other figures 2, figures 3, figures 4, and find a common formulation of extended Peterson's rules, and prove that all syllogisms from the graded cube of oppositions are valid if and only if they satisfy them. So this task is before us, and we are working on that. That's all. Thank you very much for your attention.
It's a cube of opposition, which only is different quantifiers. How do you decide how many of each of these quantifiers?
So far we have developed the formulas and the theory for selected syllogisms, for selected quantifiers, not arbitrary. But we have some propositions concerning arbitrary quantifiers. The list of quantifiers you have already seen. These are here. These are for this quantifier. So so far our syllogism concerned and have been proved only for these kinds of quantifiers, not arbitrary, because natural language is extremely extensive. So it would require to prove something for several thousands of the quantifiers, which is so far not realistic.
Thank you.
Mhm.
Syntactically, this means that any formula side, can be replaced, substitution law. And if we replace formula by its negative form, we do not change the form of syllogism. In principle, new for you, and why they are not considered as only negative substitutions or positive.
Simply the, do you want to answer?
Example, most people like I replace negation. Most, I would say, young people. Young people, it doesn't mean that they are old people. Natural language is substitute by negation, because if I interpret expression with negation by natural language, it doesn't say. As it be in the relate to placing some negation, or we can change predicate and show that it isn't safe. Yes, I understand. Yeah, so this means that because in the beginning the claim was validity. Yeah? Valid syllogism is valid everywhere in everyone. However, your explanation, is relative. Yeah, it relates to certain models. However, I mean, in principle, in the formal theory, this means that the substitution law, which I mentioned, is not useful, valid. So we shall see. Okay, so this is just because time is running. This is the remark which I would like. Okay, in any case, thank you. And I'm for the second talk given by session together with Helen Mobile. And the title, so this is again joint contribution with Victor Pavliska. And the title you will see in a moment. Again, I will not read because not enough light. Thank you very much for area of intermediate quantifiers. So I will continue in the area of intermediate quantifiers, and I will focus on verification of syllogism also by special Peterson rules, but from another way. You will see, and we can compare the
result which we proposed by Willem and also the result which we proposed with my colleague with Viktor Pavliska. You can see that as Willem said in previous presentation, there are several methods how to interpret logical syllogism. We proposed syntactical proof, we constructed model, we used Aristotle and Peterson rules from generalized point of view, and now we will continue in the direction to use special grades. So first of all, we have to define what is proposition for us. It means at this moment we have the positive expression and also negative expression. It means, to mám mačka tady? Ne. Oh. Pravé. No počkat, to ne. Tady? Tady taky ne. To nevadí, tak já to budu ukazovat. No a to mi ale přeskočí. To já nechci. Já chci laser. Toto? Okay, so we have two propositions. So it means at this approach, we will use intermediate quantifiers which form only graded Peterson square. At this moment, we are not working with graded Peterson cube, but of course, we can extend this approach for this situation. So what is syllogism we said? We have two premises and we conclude somehow conclusion. So we have four figures. It was discussed by Willem. I will go directly because I have a lot of examples and it's better to show you examples, not to go to detail to what was said in the previous example. So there are examples of intermediate quantifiers. We know we have several forms. So now what is distribution? Because in the presentation of Willem, it wasn't explained because he had several other examples and idea what was important to say. At this moment, I will explain what is distribution, which was proposed by Peterson in his book by natural language. It means in approach of Peterson, we say that a formula is on the position of subject or predicate is distributed if we have information about all members of that category. This is the definition of distribution. I will explain you in more detail in concrete example. And we say that the formula which is in the position of subject or predicate is undistributed if we don't have a complete information of all members of the concrete category. So here is explanation for classical quantifier, for the classical quantifier all. It means we have the quantifier all SRP, and we say that we have complete information about S and also about only about S. It means we know what we can say about the subject. It means for these classical quantifiers, the formula which is on the position of subject is distributed. We can see complete table of properties for the group of classical quantifiers. It means we observe first, we have only four quantifiers for better understanding. We are interested in the quantity, quality, and in the distribution of the concrete formulas. We can see that quantity means if the concrete quantifier is universal or particular. It means if all or some. Quality means if the quantifier is affirmative or negative. It means if this quantifier is in the position in the concrete sphere of the left-hand side or of the right-hand side. And also, it's based on concrete quantifiers. We can see which formula is distributed and which isn't distributed. If the quantifier all, we are working with all, that the formula which is on the position of subject, at this moment, this formula is distributed. For example, if we have negative quantifier, it means no SRP. At this moment, both formulas are distributed because we have information about both fuzzy sets. So, this is the complete table of classical quantifiers, and here are concrete rules Peterson rules which were introduced by natural language. At this moment, I have to say that these rules were introduced for basic 5 intermediate quantifiers. It means for all, almost, almost, many, and some. It means he assumed just 5 intermediate quantifiers. It means the best one, the best information we have about the quantifier all. It means this is the best distribution about the formula which is on the position of subject. It means the Peterson proposed that in valid syllogism, the sum of distributions of middle formula must excess the number 5. And we can see, of course, other examples of rules. And as Willem introduced, we proposed mathematical definition of this expression of natural language for intermediate quantifiers which are based on evaluative linguistic expression. It means these rules, which were proposed and explained in the previous presentation, work for intermediate quantifiers based on definition of intermediate quantifiers using evaluative linguistic expression. But in our approach, we have a more general approach because we don't have, or we don't assume only this kind of intermediate quantifiers. We can assume arbitrary quantifiers which fulfills the concrete properties. I will explain. So here I would like to explain what does it mean, the distribution on concrete examples. We assume this example with 2 particular quantifiers, f, as you can see in the previous slide, the distribution of middle formula must excess 5. It means in our approach, as I explained on the concrete table, middle formula here for the quantifier sum, distribution index in this first premise is equal to 1. Similarly, in the second premise, there is mistake, here must be 2. It means that this rule doesn't hold, and just immediately this example of logical syllogism is not valid, because as Willem explained, all rules must be satisfied for every syllogism. So now I will go to concrete our approach. So first of all, we have to say what does it mean if the quantifier is affirmative or negative. It means we propose special formula and using this special function, using this definition, we can say that, for example, if some proposition is affirmative, we define this formula is equal 1 and opposite is 0. It's very easy definition. So now we have to say what does it mean, the quantity of concrete quantifiers. It means we can see that the quantity, it means how big is this quantifier, or how many we obtain, for example, people or I don't know what, is the real number between 0 and 1, is some real number. Of course, we need to say that the quantity of the first quantifier is less than or equal to the second one if and only if for this proposition we assume this superlative property. This property was explained by Willem. It is represented in logical approach by implication. So the third property means that if the quantity of some quantifier is strictly greater than 0.5, then this is true if and only if the quantifier which is positive and the quantifier which is negative fulfill the property to be contrary. And the last property means that if we assume that the sum of both quantifiers is strictly greater than 1, at this moment these pairs of quantifiers fulfill the property of contradictory. So, and now at this moment what we have? We can assume here several examples of quantifier. At this moment, I prepare presentation with intermediate quantifier, but we can assume, for example, proportional quantifier. We can assume fractional quantifier. For example, if this quantifier fulfill these properties, it means we have the best one quantifiers and its grade is equal to 1, it means some real number from interval 0, 1. Similarly, we can define some grade for the quantify almost all. And we assume these inequalities, which must be fulfilled. It guarantees some monotonous position of quantifiers. It's similar in our approach where we can propose monotonicity theorem based on expression of a relative linguistic expression is the similar. So here we explained for these two grades this property which guarantees out the contradictory pair, and also this property guarantees contrary pair. So and now distribution. What will be distribution in this approach? We have to say if somehow say if our formula is on the position of subject or in the position of predicate, and at this moment we can define some distribution. It will be function at our approach such that the quantitative or our quantifier, or no, if the concrete formula is on the position of subject, at this moment distribution is equal just to quantitative of the concrete and quantifiers. If the formula is on the position of consequent and our proposition is affirmative, at this moment the distribution will be equal to epsilon. And similarly for the quantifier, if the proposition will be negative, the distribution index is equal to 1. Now, this is definition of distribution index. It means, if I said the distribution index is equal to quantity if we assume the formula on the position of subject. Similarly, as I explained in previous slide, we can observe the situation of the position of consequent for concrete affirmative or negative proposition. So now here we can see how the concrete rules of distribution quality and quantity looks like. In the approach, okay, I don't have enough time, maybe we can discuss later. In our approach, we assume that the rules of distribution, it means here is the expression of natural language. In our approach, it means that Lukashevich conjunction of both distribution indexes for a middle formula on the position of subject must be strictly greater than 0. Similarly, we can define other rules, or maybe we can discuss later what does it mean, these rules, because I don't have enough time to explain it. But here I prepared some examples. Maybe here it will be better to observe what we have. So, for example, here we assume the syllogism of figure 1, and we know that the syllogism will be valid if and only if the first 4 rules will be satisfied. At this moment, we can observe on the first premise the middle formula on the position subject for the quantifier all is equal, distribution equal is equal just the quantity of this quantifier, which is equal to 1. And the distribution index for this formula, which is on the position of consequent, is equal to epsilon. It means we obtain the first rule of for distribution index is satisfied. Similarly, we can interpret other rules for several other examples of logical syllogism. I have here a lot of more examples, but I think that I don't have enough time to go to detail for all examples. So I stop this presentation. Thank you for your attention. I hope that I don't know if I'm in time. Aha, okay, it's no problem. I will prepare here. So, what is a message from this presentation? From this presentation, it's very nice to see that we can interpret or verify validity of logical syllogism using these extended Peterson rules for several kind of logical syllogism with several kind of quantifiers, not only for intermediate quantifiers which are proposed by Willem and myself. And for the future, of course, as Willem explained, it's good to continue in the graded cube of opposition, of course, to find the rules for syllogism for the second phase and also in the cross of this syllogism. This is now for us just open problem. Okay.
Quantifiers. So I've been studying some research which does them in a categorical sense, mainly the for all and there exists quantifier and it can be seen as adjoint functors between categories of formulas. And this yields a natural duality of for all and there exists. Do these intermediate quantifiers also have this duality?
Duality, you mean?
The form of pair for all and there exists. Do these intermediate quantifiers also naturally form pair with?
I think that in our approach we don't have duality because we cannot change negation from the inside from the formula to outside. If I understand your question.
Quantifiers, yeah, without going inside, yeah, actually.
Do you think these approaches can be harmonized?
Well, maybe why not? Of course, but at this moment we don't.
Yeah, because actually, yeah, so all your syllogisms can be cut in the middle, yeah. So using, for example, the middle level is quantifier many. Yeah, and then yeah, the upper part is in a certain sense is dual to the.
Yes, I understand what you mean, but in our approach, if I take all and some, there we cannot assume duality because some in our approach is defined using classical conjunction. And if I negate in our approach Lukashevich conjunction, Lukashevich implication, I obtain Lukashevich conjunction, not classical conjunction. But there are approaches, for example, of Dubois Didier. In his approach, he assumed just duality of these quantifiers. But in our approach, we don't assume duality. My nemáme konjunkci Lukaševičovu, víš, sam.
So yeah, I will answer the question going to be limited to time. And then now line will go Dr. Boris.
Yes.
Yeah, yes, I'm sorry.
Yeah.
Yes. Right, yeah. Very satisfactory one. And signal temporal logic formula. You have the floor, yeah. I will give you the full time within the rules.
Okay.
Okay.
Thank you very much. So, hello everyone, I'm Joris Thier. I'm from FSTA Paris, and I'm very happy to be here. My background is more on robotics and formal methods fields. So I like working with fuzzy logic, but I think I have a lot to learn. So I'm very happy to be here. And I'm happy to present this work about fuzzy satisfaction of a signal temporal logic formula. So just to know, does anyone know about temporal logic? No? Okay, I will explain that right now. So what is temporal logic? So when we look at critical systems, we want to specify and have guarantees on some constraints on our systems. And to specify such constraints, we don't want to use natural language because of ambiguity. So we have a formalism which is called temporal logic. we can deal with spatial or state constraints. For example, we want our system to stay in a safe zone or to avoid an obstacle zone, or something like the speed must stay below maximum speed. And also temporal constraints. So we can specify that we should never go in this place if we are not if we have not reached a previous area before. So there are two main uses. The first one is monitoring. So in system verification, so if we have a system that is running, we want to monitor in real time if everything is okay, and if something is bad, to raise a flag and stop the system, for example. We can also do some control design, so for example, trajectory generation or model predictive control. So we have a system we want to design, we have the specifications, and we design the system with respect to the specifications thanks to that. So very short history. The linear temporal logic was first introduced in 1977 by Amir Noeli. It was mainly for formal verification of computer programs. So only discrete time and discrete values. And then in 2004, Oded Mahler and Beren Nikovic introduced the signal temporal logic, which can deal with a real-time system and real-valued constraints. So this is our interest because we can deal with cyber physical systems, so mainly robots. So this is the signal temporal logic syntax. So I have a formula phi, which can be Boolean, so the true or false Boolean. It can be an atomic predicate. Basically, it's a state constraints like x1 plus sinus of x2 is greater than 0. You have the operator, the logical operators from first order logic, so the not, the and, the or, etc. And you have the main temporal operator, which is the until. So phi1 until the time interval t1, t2, phi2 means that phi1 must stay true until time t prime between t1 and t2, where phi2 is true. In other words, phi2 is true somewhere in between t1 and t2, and every time before phi1 was true. Okay, we can derive two other operators, the finally operators, which just say that phi must be true at a time during t1 and t2, and the globally, where phi must stay true during the whole time interval. So I will give some examples. First example with a trajectory generation to illustrate. So this is a very classical problem, the reach avoid problem. We have an obstacle in gray, and the target we want to reach in green. And we can specify this mission like that. So globally, we have to stay outside the obstacle. And finally, we have to reach the target. A little more complex example. Here I have, let's say, a robot that is a low battery. So it needs to charge itself. There is a charging station in green. But in the environment, there is a puddle. And if it's very dangerous to bring water in the charging station. So either I avoid the puddle, so the blue trajectory here satisfies the formula, or I can go through the puddle, but then I need to go to the carpet before going to the charging station. So this is specified like that. Finally, if I reach the puddle, then I have to not go to the charging station until I reach the carpet. And finally, I need to reach the charging station because I am low battery. So another example here with different configuration. So here I go through the pedal, then to the carpet, and then to the charging station. So I satisfy my formula. Okay, in this work, we are interested in dealing with uncertainties because we are dealing with robots, and robots are an uncertain system, and we want to be robust to uncertainties. So the first thing we can do, so this is a reach avoid example. I can compute the optimal trajectory, but I never want to ask a robot to follow this trajectory because it's way too risky. I have too risky to because of the collision. So in the state of the art, there are different approaches, mainly stochastic and risk-based approach. So I compute robustness delta, and I guarantee. Well, it's not a guarantee. I have a probability of success of satisfaction of my mission, like 95% of avoiding the obstacle or something like that. Another approach is to use bounded uncertainties. So here I assume that I can bound my uncertainties, and then I compute what I call the tube. So it contains every possible trajectory, and if I prove that this tube satisfies my formula, then I'm sure that that the formula is true, and that's what we want, because there is a guarantee behind that. So if I take a little example, here I have a tube in blue. So it is a one-dimension example. The time is in abscissa and the value in ordinate. And so at each time I have an interval of possible value for my system. And I'm interested in knowing if I am greater than a parameter, a fixed parameter that is here, rho. So before T1, it's quite easy. Wherever I am below rho, so I do not satisfy my formula. After T2, I satisfy it, but between the T1 and T2, there are both possibilities that I satisfy and that I violate the formula. So there are two main results in the literature. The first one uses a three-valued logic. So it say in the middle, in between T1 and T2, is undefined. We don't know if we satisfy or not our formula. And another result that is more conservative and just saying it's false using Boolean approach. But in both cases, we lose information and uncertain result. And in this work, we want to have like a measure of satisfaction of our signal. So this is what I want to present now. So there are too many interests to introduce fuzzy satisfaction of FSTA. The first one is the one I was talking about. It's to have a measure of how much we are close to satisfy a formula or violate it. And the second one is to improve the expressiveness by combining predicates as desired. So I will come back on that just after. So first I need to change a little the syntax of the STL. So you have two new guys here, the alpha and the pi. So the alpha is, so I have no more Boolean value here. I have a satisfaction score between 0 and 1. And the pi is my set predicate. So here it will be a set inclusion test. So I want to know if I am inside, so it's a 2D example, inside the box or outside the box. So if I am fully included, I want to have a score for true. If I am fully dejoined, I want to have a score of 0 for false. And every other configuration, I want to have something between 0 and 1 and closest to 0 if I am not very included, and closest to 1 if I am almost included. So how can I do that? I use this formula by using the volume of the intersection and the volume of my states. And so I have the 1 for if I am fully included, 0 if I am fully dejoined, and something that that is close to 1 if I am almost fully included, etc. For the other operators, logical operators, I have the equivalence. So for the AND operator, I can use minimum. For the not 1 minus, and for the until operator, I have also an equivalence by using the shift operator, which is just shifting in time of my signal. Okay, if I take an example, here I have simulated a system, a hybrid system with a library which is called Dinibex, which use ground integration computations. So I have a tube in blue. And so this is the system is like a car that is only turning on left or right, and that sometimes we change the directions. So that T1 we turn right, 32, we turn left. We have an obstacle we want to avoid, a target in green here, and a waypoint we want to pass through. So I specify the mission. Finally, I want to reach the waypoint in less than 5 seconds. And I want to avoid the obstacle, and I want to finally reach the final target. So if I use the equivalence I presented just before, I have this expression. And here I avoid the obstacle perfectly, so I have 0 for the obstacle, 1 for the final target. And the waypoint is almost reached, so I have a score of 0.71. So I have a measure of how much I satisfy the formula. There is a possibility I miss the waypoint, but there are a lot of possibilities that I respect my formula. Okay, now I want to introduce score functions to extend the STL formula syntax. This was the second point of the interest of this approach. So in the previous example, I used this expression as an equivalent of my formula. And I can say this is a function, I call it sigma, of my predicates. And so this sigma, I call it a score function. And I can write some specification thanks to that function. So some examples. Here, let's take an example of a mission where I need to follow some waypoints. And let's say I want to specify that I want to reach at least the half of the waypoint. So if I set here the alpha at 0.5, the formula says that exactly I want to reach half of the waypoint. I can add a weighted sum, so I can ponderate my waypoints. If I have a waypoint that is more important than another, it can be very useful for robotic calculations. And the last example, where here I specify that I allow to miss a waypoint, but never 2 waypoints in a row. So in other words, 2 successive waypoints cannot be both related. So if I take this third example, I call it mu, the value here. And I simulate the same system as before and give some examples. So I have 7 waypoints now. So the blue trajectory is perfectly reaching every waypoint. So I have a score for each predicate of 1. And so my final score is 1. So I satisfy perfectly my formula. I am sure there is a guarantee that I satisfy my formula. The second example with this trajectory. So here we have only 1 waypoint we may miss, but the score is very high. So we are greater than 0.5. So we say it's okay, we validate our formula. Another example where we have a score which is very low because we missed 1 waypoint and we almost missed the previous one. So the score is very low and we say we do not satisfy the formula. And the last example where we miss the 2 first waypoints, so we do not respect the condition of the formula. And even if we reach every waypoint at the end, we have a score of 0. We are sure we do not validate our formula. So to conclude this work, this approach allows to deal with bounded uncertainties. We introduce the score functions to add more expressiveness compared to just classical STL. And we have a guarantee on the obtained satisfaction score. If we obtain a 0 or a 1, we have respectively the non-satisfaction of the satisfactions. For future work, this is a work in progress, so I have to continue the implementation and provide some more examples with applications. And in the literature, there are already fuzzy temporal operators, which are like the fuzzy is on the temporal, the time intervals of the time operators, like we have the almost always instead of the globally. So I'm interested in adding that in my work. That's it for me. Thank you very much for your attention. Yes. I consider every possible trajectory. Sorry, can you? Yes. Yes. I'm not sure to understand. Yes.
Description, yeah, that relates or vice versa. You have description using the formula, but you can propose more than one trajectory that can be somehow optimized using this formula.
Yes, maybe it was a bit misleading. When how can I say? About fuzzy satisfaction, I have a tube, so a trajectory, but with bounded uncertainties. And I consider the whole tube, I don't know where is the actual trajectory. And so I try to measure if the trajectory will satisfy or not. It's one, but I don't know it. So I consider every possible trajectory within the tube. I know the tube. Where it is something like that. So for each time, I have an interval or an interval vector that I know my trajectory inside this interval, but I don't know where it is. So like that, yes.
Yeah. The title linguistic interpretation of natural data using forms of intermediate.
Okay, thank you very much. This presentation will be devoted to application. It means I will explain you how our quantifiers, which were explained in Willem presentation, can be used for an interpretation of natural data and how we can obtain some expression of natural language from the natural data. I think that I can switch some slides because we had two big presentation about intermediate quantifiers. Only motivation, of course, we are working with several data from many areas, and the idea is to use or to somehow explain or interpret the data using natural language. Here are expression of examples from economy, from for example, from other areas, we can of course introduce several examples. It was discussed in previous presentations. So as I said, we use these three main theory. It means theory of evaluative linguistic expression, theory of evidence rules, and the theory of generalized quantifiers, mainly using intermediate quantifiers we will work. As I said in my presentation, we are working with Lukashevich algebra, so I think that I cannot go to the detail. Here here is explanation of evaluative linguistic expression. This slide it's new for this audience. It means we can see that we are working with the expression of natural language, small, very big, and several other examples of expression. But what is important is that we assume the basic trichotomy, which is it means we work with the expression small, medium, big. Here we can see on this picture how we can interpret in a concrete model this evaluated linguistic expression. It means here we can see that we are working with the fuzzy set small, and we can modify this expression by several hedges. So it means we obtain several examples of evaluated linguistic expression. I think that this is understandable for you because we discussed several examples today with the quantifiers. Here I prepared some examples from the area of well-being because we are working on this special project. It means that I prepared example with the quantifier most and with the quantifier almost all. And we can see that this is, for example, which is positive in our approach. And this is example of negative sentence from the area of well-being. So here is the concrete application because I think that it's good to understand how our quantifiers can be used in the concrete examples. We prepare with my students special application. We use a special data set of pingies from this station from the R package. We apply 345 observation and also 8 variables. We can see there is a demonstrative illustrative example what we have. We have the set of these data. It means we have data which are devoted, for example, bill length or bill depth and several other examples which we assume. So what does it mean? It means that we are working with the concrete context for this natural data. It means we are working with this assumption. It means we know some left-hand value, right-hand value, and also some middle value. We can see here that we can assume these concrete values from our package. It means we are working with these, for example, examples of flip length. And the idea in our approach is to somehow transform this data to the truth values. It means here is the other example. It means we assume fuzzy Guha method, which was at first proposed for classical approach by Peter Hayek, and later at our institute we proposed approach which is devoted to fuzzy approach. It means by this special method, based on concrete context and based on evaluated linguistic expression, we can transform crisp data to the concrete fuzzy set. It means we obtain truth values, for example, for this expression of natural language. It means we transform crisp data to the value of truth value for the concrete evaluated linguistic expression, and we can use in the concrete example our intermediate quantifiers which were proposed by Willem in his approach. We can see if we have concrete mathematical definition and we have concrete fuzzy sets, we can calculate the number of the quantifiers in the concrete model because we have concrete mathematical definition. Here we have Lukashevich implication. Here is classical conjunction, and using interpretation this formula in the concrete model, we obtain this degree. So now at this table, we can observe that using our package, which was proposed in our institute, we can obtain these examples of natural language with several examples of intermediate quantifiers. It means we can see that we obtain expression, for example, in the negation on the antecedent, and also we obtain examples with the negation in the consequent. It means this expression of natural language relate to graded cube of opposition which was presented by Willem in his approach, and we obtain concrete degree for the concrete quantifiers for the concrete expression or example of natural language. It means we obtain several interpretation using intermediate quantifiers of our natural data. And we can observe that, for example, here we obtain this result. Of course, we obtain several examples of this expression, and what we can do. We can use, of course, theory of linguistic reasoning. It means we can apply several examples of logical syllogism. We discuss a group of syllogism. We know that we have several forms of logical syllogism which relate to Peterson square, to Peterson cube of opposition, and from our interpretation from the natural data, we obtain some new result, new conclusion, using the concrete forms of logical syllogism. And then, of course, we can compare our result with the concrete result which can be obtained from the natural data. So it means what we can see, we can calculate definition of or concrete intermediate quantifiers in our model. It means if we have concrete data, we obtain true value of concrete quantifiers. We can use logical syllogism to obtain a new result, and of course, we know how to transform this data and to interpret this data using natural language. So it was a short presentation about application of our quantifiers in the concrete example of natural data. And for future, we would like to show or use other structures of logical opposition. For example, graded hexagon of opposition. We don't discuss this special structure today, but we know that there is possibility to use other forms of intermediate quantifiers and to use these quantifiers for interpretation of natural data. So that's all. Thank you.